Let's say we're interested in finding the area under a given curve. For this first function, we see maybe the function f of x equals 20, because we have a constant line at 20, in the range from 0 to 2. And we would like to find the area of the shaded region. We would like to find how much of the blue region there is. Well, hopefully we all know that this is a region that looks like a rectangle, and so your first step would be, well, this is 20 here, 20 up. This is 2 over, even though the picture is a little ugly, and 20 times 2 is 40. So in that case, we all know what the area under the curve is. But if we have a more complicated shape, like this one here, which I don't know the function exactly, it might be a piecewise function because each piece looks different. I could use all of the information I know. I could start by finding the area under the curve of this triangle. And this triangle we see has a base from 0 to -5, so we have a base of 5. And it goes up to 6, and we hopefully all know the area of a triangle formula, which is 5 times 6 over 2, base times height over 2, which is going to be equal to 15. So that the area of that triangle is 15. Then the next piece, we see that we have something that goes up 3 and over 6 and looks a little bit like a circle. So we see that that is probably a circle. And we remember the area of a circle formula, which is pi r squared. And so our radius here is going to be 3 because there's a radius of 3 and here's a radius of 3. And so we have pi times 3 squared, pi r squared over 2. Now keep in mind I did the divided by 2 not because the area of a circle is pi r squared over 2, but because the area of half of a circle is pi r squared divided by 2. And so in this case we get 9 pi over 2. Then we have another triangle. I could cut this piece off. And in this next triangle I have a triangle with base 2 and height 4. So we get 2 times 4 over 2, which is 4. Then we have another piece which still has a height 4 but has a base 8 to 12 is 4. The difference between 12 and 8 is 4. And so we get 4 times 4 is 16. And then in the last case, we have a little bit more of a weird situation. We have this piece, which is not a triangle. In fact, I don't know the area of that shape, but I do know the area of this shape. The bottom shape here is a rectangle. 16 minus 12 is 4, and it has a height of 4. So again, we have another 16. 4 times 4 equals 16. And then the upper part, we have from 12 down to 4. 12 down to 4 is a difference of 8. So the height here is 8. And the base is 16 minus 12, which is 4. And so we get 8 times 4, which is 32, divided by 2, which is 16. 32 divided by 2 is 16. And so in the end, the area under this whole shape is going to be 15 plus 9 pi over 2 plus 4 plus 16 plus 16 plus 16. The sum of which is 10, 20, 30, 48, 52, 62, 67, so we get 67 plus 9 pi over 2. And so we see that we have the area under this curve, which is 67 plus 9 pi over 2. We see that it can get pretty complicated once your function is not a super simple function. And in fact, if we go back to a simple function, if we have something that's just a simple, it looks like exponential growth here, and we want to find the area under this curve, we're stuck, right? We could estimate, say this point was A and say this point was B. We might be able to say, okay, we have a triangle that we know would be an overestimate of the area under this curve. But we don't know for sure. We don't know the area under this curve. And so we're going to employ calculus to find the area under this curve. And when we employ calculus, we're going to do it in a simple way. We're just going to estimate the area under this curve by taking little rectangles. We're going to take little rectangles that estimate the area. And if we find the area of all of these little rectangles, we'll find an estimate for the area under the curve. And then what we can do is we can take a finer number of rectangles. And we know that calculus allows us to deal in the infinite. We can take infinitely fine rectangles, which ends up allowing us to find the exact area under a curve given a function.